All right, so we've looked at what happens if we take a reading every minute, right? So you can actually sort of give that a name. So here we can say, like in this example, we can say we actually had the time intervals delta t is 1 minute. And so we ended up with n equals 5. You can think of it as rectangles, time intervals, or rectangles that we end up adding up to estimate the total distance traveled. So yeah, so these are standard. Delta t is sort of standard for the time interval, or the delta x. If the x-axis, if the horizontal axis was x instead of t, we'd say delta x. And n is sort of standard for just counting the number of time intervals and the number of rectangles. So we could ask, what if we actually took more data? What if we actually took readings more quickly than every minute? Like, what if we did every 30 seconds? So here, what if we said delta t was 30 seconds, which is really 1/2 of a minute. 30 seconds, right? So if we did that, you'd all of a sudden pick up more data points here. There'd be like, I'd have to put more hash marks on I'm doing this on the bottom left over here. So I'd put more hash marks for every 1/2 second, and I'd get more data points in between these, right? And so maybe it's something that's still kind of increasing nicely. But then what would happen is you would have, so let's just say we're doing a left sum again. Oh my God, oops, that's not what I want to do. You would have a rectangle like this, and then, so only for the first 30 seconds would you consider yourself to be going 60 feet per second. The next 30 seconds, you might be going, let's see, this one was 200. So let's say this is like 150 or something, and then this is 60, right? So if you think about this very first, the first rectangle here, this would be delta t is 0.5. So the rectangle, let me just zoom in on it. So the rectangle right here would have, would be the distance traveled in the estimate for the distance in the first half minute, first 30 seconds. So the distance in the first 30 seconds would be, what would it be? It would be 60 feet per minute times 1/2 a minute. So that would be 30 feet. And then similarly for the next 30 seconds, that would be this rectangle right here. So the next 30 seconds you would have 150 feet per minute times 0.5 minutes. So that would be 75 feet. Okay, so then, and then you would just keep going. In fact, so then you would have this rectangle here. This is few enough that I can draw them all. If you think about it, how many rectangles are we going to get? You should be able to sort of say how many rectangles we're going to get. Total, oops, so that's like that. Again, notice if this is a left sum, that very last data point of 420 is not actually used. But so here we have delta t is 30 seconds, right? Or 1/2 of a minute. And the number of rectangles is 10, because we basically say we're right twice a minute for 5 minutes. And so we have that, right? And what this should be is this should give you a better estimate. Notice that it's somehow like taking more readings. Taking more readings should somehow give you a better estimate. You have more data, you're sampling it more often. This is a left sum. You could do a right sum also and get another estimate. That's maybe an overestimate again, and you could average them. So you can sort of see what happens. If we take more data, we get better estimates. You could imagine, let's just go over here. You could imagine, what if I took an estimate every second or something? So if delta t was 1 second, which is really 1/60th of a minute, right? You could then imagine, well, now I have data almost like I have like 60 points or 59 points in between each. So all of a sudden I'm getting data every second. That's a lot of readings. How many readings is it? Well, 60 per minute times 5 minutes. So that's n equals 300. And okay, let me pick a different color. So what you would have now is you would have these like very thin rectangles, and even, I'm just going to zoom in even more, like, and this is even like not even close to thin enough, because there should be 60 of these, but I'm just kind of drawing what you get, right? And what you see is you should get a better and better estimate, sort of, you know, et cetera. I'm not going to keep drawing those, but you get 300 little rectangles. The sum of the areas of all of them is a nice approximation of the distance traveled. And what's this looking more and more like, if you just think about going on, I guess there's some ones at the very end also. Oh, yeah. And so on. What you can imagine is that you're going to get a very good estimate, and it's also like looking like the area under the curve, because you have this sort of total, you're sort of getting a better and better, there's sort of a curve made up by the velocity function, and you're getting the area under it. So good estimate of the distance, but also of the area under a curve. And so that's why we're starting to realize that, oh, distance might have something to do with the area under a curve. In fact, if I wanted to really, I can't really draw this well, so I just ripped this out of the book. Ignore these. This is a different question, so the time and the velocities aren't really right. But it's sort of a similar type thing, right? This is with a certain number of rectangles. You can actually see the left and the right sums here, right? You can see sort of the left sums are these like darker, these slightly darker rectangles are the left sums, and then the lighter ones that go like over are the right sums. And this is even like more and more rectangles, but so first off, it's giving you a better estimate of the distance traveled, and it's giving you the area under the curve. And so the idea here is that the distance traveled equals the area under the velocity curve. We're sort of approximating two different things simultaneously, so they must be equal. We're approximating the distance traveled just with these rectangles, just rate times time, but we're also approximating the area under the curve. So that's kind of the big idea. It's really one of the most important ideas of this, is that if you want to estimate the distance traveled by some object, and you have a velocity function, because that's what this dark blue line is, right? It's like the velocity function for the situation. Again, ignore these numbers because they're not right for the situation, but it's vaguely similar. Then you'd actually get the area under the curve equals the distance traveled, and that's kind of the big takeaway from this line of thought. Okay. Next, I'll show you what happens if we actually have a specific function, like given a formula for a function. We could sort of do the sort of sum of the rectangles, which is called a Riemann sum. I started to say Riemann sum. Or we could just try to get the area directly if the function is simple enough. And so I'll show you that next.